In this lesson, we're going to talk about combinations of functions, and specifically we'll focus on composition of functions. But first, let's look at some general combinations. So let me use an example with f of x equals x squared and g of x equals 1 minus x, a parabola and a line. Let's find each of the following. What if I asked you to find f plus g of x? Well, it's exactly what you think it should be. You're just going to add those two functions and combine any like terms. Now, there are no like terms, and then it's generally accepted that you're going to put it in descending order, so I'd probably write my final answer like that. Okay, what if I asked you to find f minus g of x? Well, likewise, we're just going to subtract these two functions, and there's no like terms. So notice we did x squared minus, and then g of x is 1 minus x. So I have to distribute that negative sign. And so I'm going to get x squared, a negative 1, and a plus x. And once again, probably put it in descending order. Although it's not incorrect because it didn't say you had to put it in that order. All right, what if I asked you to divide these two functions? Well, we know how to do add and subtract. Why would divide be any different? It's just going to be x squared over 1 minus x. We can't cancel anything. We can't factor anything. So that's all we can do with it. And then lastly, what if I asked you to multiply f of x times g of x? And so in that case, we're going to multiply x squared times 1 minus x, and you'll distribute, and you'll get x squared minus x cubed. And if we put it in descending order, we'd say negative x cubed plus x squared. All right. Now let's look at composition. So what if I had f of x is x squared minus 4, and g of x is the square root of x plus 1? Graph f of g of x. So for composition, we're going to take this inside function, and we're going to send it to the f function. So the input to f will be whatever g is. So we're going to replace the square root of x plus 1 everywhere in f where we see an x. So that's going to give us f of the square root of x plus 1. And then when I plug that in, I'm going to take that square root of x plus 1, and f squares that input and then subtracts 4. And so when I square it, that cancels the square root, and we're left with x plus 1 minus 4. And then we simplify and we get x minus 3. Now before I try and graph that, let's take a look at the calculator, and let me show you how you can do composition on a calculator. So I'm going to go into y equals, and my calculator's being stubborn on me. So let's trick it into getting to work. There we go. All right, so I'm going to go into y equal, and in y1 I'm going to put x squared minus 4. And then in y2 I'm going to put the square root of x plus 1. Now, I don't want to graph either of those, so I'm going to go up and I'm going to highlight over the equal sign and press enter, and then when I hit down arrow, the equal sign is no longer highlighted. So if I press graph, it's not going to graph y1. I'll do the same thing with y2. I don't want to graph that either. And now what I want to do in y3 is I want to do f of g of x. So f is my y1 and g is my y2. So I want to do y1 of y2. So I can get the y1 two different ways. One way is to find the vars button. That's highlighted there in red now. In the vars button, hit the right arrow to go to the y-vars submenu. And then we want to go into function because we're graphing in function mode. And there's y1. And then I want to put parentheses. So that's like my f, and then parentheses. And then I want to do g of x, which is y2. Now, on some calculators, depending on your operating system, there's a shortcut to get the y1 or y2 or y3. And so I'm going to press the green alpha key, and then I'm going to press the trace button along the top row. And that's a shortcut to all these y1, y2, y3s. So I'm going to select y2. So this says take y2 and send it to y1. And then I'll put parentheses x. And now when I graph, and I'll hit zoom 6 for the standard window, notice it graphs x minus 3, but it doesn't graph the entire line. It seems to stop at x equal -1. Why is that? All right, so when we do composition of functions, we have to analyze a little bit and look at our domain. So the first thing I want to do is look at this inside function g of x. So what is the domain of g of x? Well, that's the square root, and we know we can't take the square root of a negative. So we know that the x plus 1 has to be greater than or equal to 0, which means x has to be greater than or equal to -1. Then we look at the f function, and that's just a parabola. There's no restrictions on that. So I know that I want to graph the line y equal x minus 3, but x has to be greater than or equal to -1. So part of that line I'm going to erase, and there'll be a closed circle at -1, -4, because x can't equal -1. And then we'll have the line going to the right with an arrow at the end. So that's the tricky part when you do composition, is you have to consider the domain. What if I asked you to find g of f of 2 root 3? Well, let's write down what those functions were again. F of x was equal to x squared minus 4, and g of x was equal to the square root of x plus 1. So to do g of f of 2 root 3, I need to take 2 root 3 and send it to the f function. So I'm going to put in here 2 root 3. So f of 2 root 3 is equal to 2 root 3, and then f squares that input and subtracts 4. Now when I square 2 root 3, when I square the 2 I get 4. When I square the root 3 I just get 3. And so I'm going to have 4 times 3 is 12. And then 12 minus 4 is 8. Then I'm going to take that 8 and I'm going to send that to the g function. So then g of 8 is going to equal the square root of 8 plus 1, which is the square root of 9, which is 3. And now we've evaluated it. All right, so composition of functions. The notation we use is either f and g in parentheses with a little circle in between them, and then an x in parentheses after it, or more commonly, f parenthesis g of x and then close parenthesis. So either notation is fine. It's important to understand this statement though. The domain of the composition is the set of all x in the domain of g such that g of x is in the domain of f. So we have to first consider what's the domain of g, and then we have to think what are the outputs of g, and are those acceptable to be inputs to f. And we'll have some examples to show just exactly how that works and how it can be complicated at times. So let's look at these two functions. F of x is x squared minus 1. That's a parabola opening upward, shifted down 1. And then g of x is the line 3x plus 2, a y-intercept of 2 and a slope of positive 3. So we want to find f of g of x. So what I want to do is I want to take g and plug it into f. So I want to take 3x plus 2 and evaluate that according to the rule that f gives us. And what f does is it squares the input and then subtracts 1. So I'm going to take this input, 3x plus 2, and square it, and then subtract 1. Now remember, when you square it, you're multiplying it by itself twice. So that's where you have to distribute or FOIL, as some people were taught. And I'm going to get 9x squared plus 12x plus 4. And then don't forget the minus 1. And I can combine like terms. So my final answer will be 9x squared plus 12x plus 3. And now I have to go back and consider the domain. So let's look at g of x. That's just a line, and that can accept any input. So x could be all real numbers. X is an element of the real numbers. And then f of x, that's a parabola. That can take any number as well. So there's no restrictions on either of these functions. So I don't have to specify any restrictions on my answer. And that's it. So that was a simple one. All right, let's look at this one. This one's a little more challenging. What if f of x is the rational function x minus 5 over x plus 3, and g of x is the line x plus 4? Find the domain of f of g of x. So it's not even asking us to figure out what's f of g of x. It just says what's the domain. So let's start with g of x. What can g of x accept as inputs? Well, x can be any real number. So that doesn't seem to be a problem. But now when I take my output from g of x and I plug it into the input of f, there and there, do I have any issues? Well, yeah, f is a rational function. And I know that I can't divide by 0. So f cannot accept, let's write it here, f cannot accept the input of negative 3. Because if we put a negative 3 here, we're going to get a divide by 0. So the question is, what output from G causes a problem? And so obviously, G cannot output a negative 3 and send it to F, because then F will be a divide by 0. So what causes G to output a negative 3? Well, when would this give you a negative 3? Well, if I subtract 4 to the other side, x cannot equal negative 7. So if I tried to actually evaluate f of g of negative 7, I'd send negative 7 to g, and that would give me negative 3. And then I would try and do f of negative 3, and I'd have a problem in the denominator. I'd have a divide by 0. So the domain of f of g of x is going to be all real numbers except x cannot equal negative 7. So you may need to go back through that one more time just to make sure that that's clear in your mind how we found that. All right, let's look at another example here. I'm tired of using f and g, so let's use h and m. H of x is 1 over x squared. We know that x can't be 0 in that function. M of x equals 1 over x minus 1. We know that we can't do m of 1 for that function. So find h of m of x and m of h of x. Notice I used the different notations. Here I used the parentheses, here I used that circle, just to show you that there's two ways of writing it. All right, well, let's start with h of m of x, and then we'll go back and think about the domain. So h of m of x I'm going to take m of x, which is 1 over x minus 1, and I'm going to send that to h, and h takes the input and has 1 divided by that input squared. So it's going to be 1 divided by this fraction squared. So 1 over x minus 1 squared is 1 over x minus 1 times 1 over x minus 1. So the 1 times 1 in the numerator is just 1, but in the denominator, I'm going to get x squared minus 2x plus 1. So now I have a complex fraction, a fraction within a fraction. And so for complex fractions, you change it from a division problem. Let me change the color of this fraction bar. Instead of doing 1 divided by that fraction, that's the same as 1 times the reciprocal of the fraction. And so our final answer is just going to be x squared minus 2x plus 1. If that seemed like some math magic, let me give you a simpler example. If I had 1 divided by 2/3, that's the same as 1 times the reciprocal of 2/3, and that's just then 3 over 2. All right. So we found h of m of x. Now let's find m of h of x. So now we take the function m and we send h to it, and h was 1 over x squared. And so m takes that input, and it's going to be 1 divided by the input, which is 1 over x squared, minus 1. So notice I'm plugging in 1 over x squared in for x right there. All right, so now we have another complex fraction. So step 1 is let's combine these two terms. And to combine them, I need a common denominator. So I'm going to change this 1 to be x squared over x squared. That's just another more complicated way of writing 1. But now we have the common denominator. So now I have 1 over 1 minus x squared all over x squared. So I combine those two fractions in the denominator. Okay, and as we saw in the last example, dividing by a fraction is the same as multiplying by the reciprocal. So then this is just going to simplify, let me do it over here. It's going to simplify to x squared over 1 minus x squared. And as you can see, here's where we're starting to see all that work you did in the previous course on dealing with rational expressions and rational functions. So it's really important that you understand the algebra involved and how I simplified that. Okay, so we've calculated those. Let's find the domain of the red one, h of m of x. So let's go back and look at the beginning. And so h of m of x, so let's start with the inside. Let's start with m of x. Do we have any restrictions here? Well, we know x cannot equal 1, because then we'd have a divide by 0. So x can't be 1. Now, once I take this and I plug it in for the x there, what do I know? Well, I know that I can't send a 0 over there, because I can't do h of 0. That would be a problem, because I can't have 1 over 0 squared. But, fortunately, there's no way this 1 over x minus 1 could ever equal 0. So all I have to worry about is that x is not 1, and then m is going to be anything else except 0, and so then there won't be a problem when I send that to h. So the domain for h of m of x is just, is all real numbers, except x cannot equal 1. Okay, now let's do the green function. Let's go back up here. All right, so the green function says, let's do purple. Start with h of x. Any restrictions on that? Well, yeah, x cannot equal 0. If x equals 0, then we have a problem. Then we're trying to do m of h of 0, and we don't even get past h of 0, because that's undefined. All right, so x cannot equal 0. Now, what about whatever comes out of h has to go in here to m? Do we have any restrictions there? Well, yeah, what's coming out of h cannot equal 1, because then m will have 1 divided by 0. So I have to look at h, the 1 over x squared, and can that ever equal 1? If it can, then that's going to be a problem. Well, sure. That'll be 1 when x is equal to a positive or a negative 1. So if I did m of 1, if I did m of h of 1, then that would equal m of, when I plug in 1 into h, I get 1. And I can't do m of 1, because that causes a divide by 0. And likewise, if I did m of h of negative 1, that would cause a problem too, because it would output a 1, and I can't send 1 to m, because I get a divide by 0. So I have a couple of restrictions here. For m of h of x, x can't be 0, and it can't be 1 or negative 1. Any other number is fine. So all real numbers except x cannot equal 0, 1, or negative 1. And there you go. So there's a lot of thinking involved. If math to you is always just show me a problem and I'll do the steps exactly like I did before, we're going to run into problems as we progress in higher level mathematics. You have to have the basic understanding of the math that you've learned up to this point, but you also have to use some common sense, and you have to understand the concepts. All right, last idea. Let's work backwards. Express f of x equals the square root of 2x plus 1 as a composition of two functions. So what I'm saying is that we had two functions. Let's call it, I don't know, g of x and h of x. And when I did g of h of x, I wound up with this f of x function, the square root of 2x plus 1. Now, there's an infinite number of ways to do this. But usually when I have students do this in class, and I give them a few minutes, a lot of them come up with the same answer, and then a few people have different answers for that. So here's one example. This would be a common example. If h is equal to 2x plus 1, and then g is equal to the square root of x, then when I do g of h of x, I'm going to take this 2x plus 1 and send it to that x in g, and I'll get the square root of 2x plus 1. So that works. That would be one way of doing it. Is there another way to do it? Well, I already told you there's an infinite number of ways we can do this. So another way you could come up with, write it in a different color, what if I let g of x equal the square root of x plus 1? And then I let h of x equal just 2x. Now when I did g of h of x, I'm going to do g of 2x, and then when I plug in 2x for that x, I'm going to get the square root of 2x and then plus 1. So that also works. So there's lots of ways that we can combine these. Usually one is a little easier than the others, but there's lots of possibilities. Could we do it as a composition of three functions? Well, that takes a little bit more thought. So what if we had, well, let's use different ones. How about r, s, and t? R of x, s of x, t of x. Well, I want r of s of t to equal the square root of 2x plus 1. And by the way, one of the obvious choices is to say, well, I'll just let this one be x and then move from there. You can never use the identity function for these. I mean, you can, but it's really silly, so I'm not going to accept those. So like in the previous example, if you said h of x is equal to x, and g of x is the square root of 2x plus 1, that's kind of like cheating. Okay, so you're not really getting at the concept of the problem here. So let's see, one thing I could do is I could say r of x equals the square root of x. And then I could say s of x is equal to x plus 1. And then t of x is equal to 2x. So then when I compose these, I take 2x and that goes in here. So then I'm going to have r of s of 2x. And then when I take 2x and give it to s, that's going to give me 2x plus 1. And then when I send that to r, I get the square root of 2x plus 1. So that's just one example, but there are many. All right, and then here's the problem set from section 1.5, starting on page 56.